white light, like sunlight, is composed of all the colors that you see in the rainbow. If I scatter white light of very small particles, then the blue light is scattered more than the red light, and we give that a name in physics. We call that Rayleigh scattering. Rayleigh scattering only happens when the particles of which the white light scatters is smaller than 1/10 of a micron. That means 1,000 times smaller than the thickness of your hair. So it has to be very, very small. If the particles are as large as 0.5 micron, then there is no longer Rayleigh scattering. There is no preferred scattering for the blue light. All colors scatter equally, and so white light scattered of particles that are 0.5 micron or larger remains white. The dependence of the power of scattering, so I'll give that P, the power, is proportional when we have Rayleigh scattering. This is the only equation that may bother you, to 1 over lambda to the 4th, and lambda is the wavelength of light. And I will not bother you to tell you what the wavelength of light is. That may confuse you. But I will tell you that blue light has a wavelength which is about 1.5 times lower than red light. And so if you take 1.5 to the power 4, 1.5 to the power 4, you get 5. And that means in Rayleigh scattering, blue light has a 5 times higher probability to scatter than red light. And I'm going to demonstrate that to you in 2 complete different ways. The first way that I'm going to do that is to make it completely dark in the lecture hall and have light going straight up here. Then I will light a cigarette, and the smoke of a cigarette has particles that are smaller than 1/10 of a micron. And so the light that you will see that is scattered off the smoke will be blue. So you have seen in front of your own eyes Rayleigh scattering, because the red light more or less goes through. It is really the blue that dominates it, that has the highest probability. So we're first going to do that demonstration to show you Rayleigh scattering of cigarette smoke. And then I have a surprise for you to also show you me scattering. But let's first do the Rayleigh scattering with cigarette smoke. This is also not a pleasant demonstration. For those of you who think that lecturing is easy, no. Okay? Going to make it completely dark, and then I'm going to hold it in there. All lights off, all off, all off. So, we all agree that this is white light which is coming up. And you don't see the light here because there is nothing that scatters it in your direction. So you don't see light here, but now look. Those of you who see blue, say, yeah. Those of you who do not see blue, say no. You better see an eye doctor. Now comes the hardest part. If I inhale the smoke and I leave it in my lungs for a minute, there is water vapor in my lungs, and this water vapor will precipitate onto these very small smoke particles. And so the smoke particles will grow they will become small water drops, larger than 0.5 microns. And that means, if I hold it 1 minute in my lungs and puff it out, you will not see blue light, but you will see white light, because you're now in the me-scattering domain. All colors scattered equally. I will tell you that just before I puff it out, and you will see the white smoke, just before I do that, I will remind you of the color that you see now. I will only do that for a few seconds, then I will remove it and I will empty my lungs. Terrible demo. Who saw the white light, just say yes. Yes. If any one of you has the courage to say no, who did not see white light? Thank you. I'm now going to explain to you, in fact, you could probably guess that, why the sky is blue and why clouds are white. Clouds consist of very small water drops, surely larger than half a micron, which is me-scattering. So the white light of the sun, scattered off the cloud, white remains white. So you now, for the first time in your life, may have an explanation why clouds are white. And you should, or may also understand now, why the sky is blue. Here is the ground, and you are here. And here is, say, roughly the top of the atmosphere. And the sunlight comes in like this. The sun is infinitely far away, so the sun comes in like this. The atmosphere is full of very small dust particles, smaller than a tenth of a micron, and even the density fluctuations of the air molecules themselves are clearly smaller than a tenth of a micron, and so you get ideal Rayleigh scattering. So white light comes in, you're standing here, but what is the light that comes to you? Predominantly blue. So the sky is blue. The light that is scattered here comes to you is predominantly blue. So that's why the sky is blue. And so the reason is simply that it is Rayleigh scattering of the dust particles in the atmosphere. If the sun is high in the sky, the total amount of sunlight that is scattered in your direction is only 1%, so it's very little. If the sun is 5 degrees above the horizon, then the sunlight has to travel through a lot more atmosphere. And so I take here a situation which is extreme when we have sunrise or sunset. So the sun is there and the light comes from this side and you are standing here. This is not to scale. This layer of atmosphere is now so enormously large that more than 99% of all the sunlight on the way to you is scattered away. So what is scattered away? The blue is gone. But if you look at 1 over lambda to the 4th, the green is gone. All colors are gone. There's only one color which has the largest wavelength, which by the way is 650 nanometers. I wasn't supposed to tell you, but I decided. So the only light that makes it through you is red. And so that is the reason why the sun looks red, and there is a cloud here in the sky, and that cloud sees light where all the low, small wavelengths have been scattered out, and so this side of the cloud is also red. You can now understand that the more pollution there is in the air, the more beautiful sunsets are. And it is well known that after volcanic eruptions, the sunsets and the sunrises are truly fantastic. It's also the moon that is red when it comes up. And even the stars and the planets, you may never have noticed it because it's not an overwhelming thing. It is the sun that is the overwhelming thing that makes the entire sky red. And so I have decided that I'm going to create in 26100 a blue sky for you and a red sunset, killing two birds with one stone. And for the physicist in my audience, I'm going to kill 3 birds with one stone. But the third bird comes a little later. I have here a bucket which is filled with sodium thiosulfate. In this bucket. And when I turn the light on, you will not even see any light from that bucket. Nothing is scattered in your direction. I think of that as being the sun, by the way. Now I'm going to add a little bit of sulfuric acid. And when I do that, very small sulfur particles, smaller than a tenth of a micron, will precipitate in that solution. Rayleigh scattering. And so the light that will come to you is blue. And you will see blue light, just like with the smoke. But now, as time goes on, we will get more and more and more and more of those 0.1 micron particles. And so the light that comes out here has no blue in it anymore. It doesn't have any green in it anymore. It's all scattered in your direction, just like here with the sunset. So what color do you think the sun is going to get? It's going to be red. That's why I said I'm going to kill 2 birds with one stone. So I will add the sulfuric acid. The difficulty with this experiment is always, if you put too much sulfuric acid in it, the whole process goes too fast. And if you put too little in it, then you will become impatient. At least MIT students would. So I'm going to put this in and stir, and then make it immediately dark. And I want you to look at the sky, which is here is the sky. If you sit all the way there, you don't see it so well. But look, how much did you pay for this? These people have a better view. So just keep looking. For me, it's already beginning to turn a little bluish. We'll just give it a little bit more time. The sun looks just white, light, as it was before. I always have a backup, you see. If this takes too long, then what I do, I add another teeny weeny little bit of sulfuric acid. To speed up the process a little. I see blue light, and when I look at the sun, it looks a little reddish already. For the physicist among you, light that scatters over an angle of 90 degrees, this light that scatters in this direction, the people who pay the most tonight, who are sitting right here, the light is also linearly polarized. That was also the case with the smoke experiment, but I didn't mention that. But for those of you who are sitting here, I can show you with my polarimeter, when I rotate my polarimeter, that I can the blue sky completely dark, and I can the blue sky completely bright again. The people who are sitting there, the angle of scattering is not 90 degrees. So they won't see it so well. But you people see it very well, don't you? 100% polarized. Look at that sun. Let's face it, isn't this incredibly romantic? In 26,100, the center of MIT, you are seeing in the lecture hall a red sunset. And in fact, the sun is so red now that I think the sunset is very close. I have given, in this lecture hall, about 800 lectures. And it is wonderful to be back here. But it really hurts to know that this is my last lecture in 26,100. I have therefore decided that I want to leave you in style. And the way I will do that is to leave 26,100 in my own private rocket. Thank you. Thank you.